Bismillahirrahmanirrahim. Assalamu alaikum and good morning. So, welcome you again. Today is the third last day of this CIMPA School. And we will have, as I told you already, that in my message, that we will finish our lectures at 1 o'clock today. And then at 1 after the lunch, we will leave for the excursion. So the first speaker of today is Professor Yero from Spain.
Good morning, everyone. I'm glad to be here again. We're speaking about more things about the dimensional labs. First of all, I want to comment something because I don't know if you probably noticed, but in the first slide, I always write the title and my name, and after appears my affiliation in Spanish. I don't know if you noticed that. Well, the reason of that is that my university required that anywhere we are going, we should write our affiliation in our language. So this is the reason that it says Departamento de Matemáticas, which is the Department of Mathematics, is the guest, Escuela Técnica Superior de Ingeniería de Artificial Technical School or High Technical School of Engineering in Algeciras, which is where I'm located, and Universidad de Cádiz. Then they say that it's not going to be like Spain instead of Spanish. Makes no sense, but just okay, today I will be speaking about some kind of variation of metric dimension which have been recently presented in which we have been working in the last week. Something like this right now. Active in the spot topic. And the thing comes, well, first there are these slides which you saw yesterday. You already know them and you will see it again tomorrow. So don't be worried about it. So right before, resolving set is this set with this property which is there. It is uniquely recognizing all distances from vertices of this resolving set, and the metric dimension is the cardinality of smallest resolving set. And here is this example. And then, well, there are some open problems which I even mentioned yesterday, some of them about the graphs having metric dimension 2, finding the metric dimension of having graphs, some other ones which are more or less the same stuff. So I want to do the self-contained with the addition that I include information that were for another topic. There are some variations which are kind of significant variations. For instance, the strong metric dimension is from the internet about it, and the strong resolving graph, things like that. And there are some other ones which are more elaborated, like this one, the resolving partitions, which is giving step to the partition dimension of the graph. What we do there is to form a partition of the vertex set, so that any two vertices are having different vertices in this partition. So how? And the partition dimension is the cardinality of the smallest resolving partition. These partitions always exist because we need to take only one resolving set and then the singletons and the rest. So always we get such kind of partitions and easy. So because I remember I have been speaking about that things sometimes, and I had immediately one question. Is partition always exist? Yeah, or they always exist. And there are some other ones, like for instance, edge metric dimension, which is more or less the same, like metric dimension, but now with the edges, but not edges, because sometimes people say that it's okay, I will consider edges, I mean, but edges that are identifying edges. But this is not the case. Here, vertices are identifying edges differently. Which is doing that, probably this is the main reason that this variation is really interesting for people. Indeed, this is, in my opinion, nowadays the most popular variation of metric. We were working in that in 2016, me and my PhD student, Alexander Kellens, well, also is also PhD student, but not mine. And we introduced that kind of considering this kind of distances for edges problem in the metric dimension. And for me, was just like one variation more. And after it attracted attention a lot. Now you can find a lot of articles doing it. Related to that is also this mixed resulting set of mixed metric dimension, which is the same, like which is more or less in the same style, but now we are considering everything. So vertices and edges should be identified, but identified by vertices, so not by edges or vertices, only by vertices. It's also very popular. People is working on it. I like it also. And both things are well in the topic of Alexander Keren's, which was in 1952. So he was working on that things. And when some problems on these things are, for instance, this variation, like you say. Remarkably is the case of this first question. The complexity of computing the partition dimension of graphs and any of the related variations, because there are strong partition dimension and local partition dimension and so on, several as well. There is no complexity study at all for any of these partitions. So I would like to work on this again. I even tried, but never succeeded. So it's not that easy. It seems that this partition dimension problem could be hard even for trees. Things serious. One good thing of this edge metric dimension, for instance, is that it's not exactly comparable with metric dimension. While always in general, when you have a variation, it always happens that you have a variation and then metric dimension is always smaller than this. Well, with edge it's different. We can find graphs in which is dimension smaller, dimension equal or larger than the edge dimension. So this is doing the problem more interesting. It would be nice to study which are the conditions that prove that these are the cases. There are examples in which infinite families in which are happening all this situation, but we don't know when exactly. Yeah, and there are other things concerning mixed dimension and so on and so on. Well, yeah, other things. This is the last one question is nice, I think. It is true that for when T is large enough, then the S dimension of the hypercube is equal to the dimension and is equal to the mixed dimension. Well, this is not exactly clear whether it is. Because it is known, for instance, that the S dimension is always between the dimension and the dimension minus one and dimension for any hypercube. And the dimension is always equal to the mixed dimension for any hypercube. And also the dimension is equal to the S dimension when D is odd. So we only need to consider the case D given. And this is kind of related with the, related with some of these variants. Now, the variant that I will consider today is something that was precisely introduced by this girl right here. Well, first, there are some other variations that you see. There are local, adjacent, CK, blah, blah, blah. Yeah. And what I will speak today is something related with multisets. Yeah. Well, this multiset dimension was introduced by these people, including here in Novia, where I know. Thomas Metric, you saw him yesterday, and the third one I do. So they considered some variation in which they are saying that, okay, until now, if we have a graph, remember yesterday I was speaking about this, when we have a graph, we consider a set of vertices, this set was V1, Vk, yeah? Vk, not Kk. And then for every vertex U here, I was forming a vector of distance, the distance from X to V1, distance from X to Vk, yeah? It's a vector, so it is ordered. Then you have an order term to have this. So the idea was simply, okay, what happens if I instead of considering a vector, I will consider a multiset? Just this simple change. Yeah, this simple change. Okay, then we'll see what happens. Okay, then we say we have a set of vertices. Now that needs not to be ordered, matter the order indeed. And then we call the multiset representation of any vertex with respect to this set as the multiset of distances between this vertex and all the vertices in this set. Of course, when we get a multiset, if we have a multiset which is 1, 2, and the other one which is 2, 1, they are the same, really. And while I am considering a vector, this is a vector, that these vectors are different. This is when some changes. So the multiset resolving set is a set such that any two different vertices of the graph have different multivectors. That means that a multiset resolving set is uniquely recognizing all the elements of the graph by means of multiset of distances to the vertices of this set. Yeah, and the multiset dimension is the minimum cardinality among all possible resolving multiset resolving sets. Yeah. So the idea is just the same like standard metric dimension, but now instead of considering a vector, I'm considering one. So the thing is changing a lot, but by a simple change. Here we have an example. We saw this graph before, but now we need not 2 vertices, but 3. Yeah, here with these 3 vertices, we form all the multisets. You see that all of them are different. So 0, 3, 2, 3, 0, 1, 2, 1, 0, and so on and so on. Yeah. So I cannot have these 2 vertices because it's not a multiset resolving set, so I need to include something more. Yeah. So this is the multiset resolving set, and the multiset dimension of the graph is precisely here. So with this idea in mind, they began to work, and we're doing few things. For instance, they were able to prove that there is no graph with multiset dimension equal to. And it is one if and only if the graph is a path. That there is the graph is a path and it is one is more or less clear. I think the idea is the same as the metric dimension because it is only one, so multisets are the same spectrum. Not much sense to speak about it because we saw it. We consider a vertex on the corner, multisets are simply distances 0, 1, 2, 3. They are having one element, so it doesn't matter if it's a vector or not. Yeah. But the one kind of surprising thing is that there is no graph with metric with multiset dimension equal to. Yeah. Why happened this? Well, this happened because of many reasons, of course, but some of them are like that. Imagine that you have a graph in which you have a set formed by 2 vertices x and y. Yeah. And that these 2 vertices are at some distance larger than 2. Yeah? Here, there are at least 2 elements. What will happen? This vertex will have some distance here, d, yeah, and to here some other, well, this is in the short stuff, yeah. And here to here will be something like, I know. Well, not I first not consider it. Have more problems. I will consider only the neighbor of this vertex here. It has distance 1. And here we have distance, which is exactly the distance between x and y, minus 1. Okay? And this other vertex, which is neighbor of this one here, it will happen to their distance of x and y minus 1, and the other one will have 1. So the multiset will be the same. Now, if the distances are shorter, then I can always find 2 vertices which are adjacent to this one, or 2 vertices which are adjacent to the other one. And so on. So I can develop a little few cases, and then we get that. This is not possible. Graph with metric with x multiset dimension equal to. So it should be at least 3 for any other graph, even for the path. Yeah. So they were doing things like that, but they immediately had some kind of problem. Which one was? For instance, consider that we have a graph that has at least 3 twins. Yeah. There are 3 twins here. I mean, they have the same neighborhood. Something like that. What will happen? They have the same, consider 2 of them, they have the same distance to everyone. Yeah. So it doesn't matter if I include the vertex or not in this, or I mean, if they are 2, then I need to include at least one of them in the set. But if they are also these 2, I need to include at least one of them. And for these 2, I need to include one of them. So I need to include at least 2 of them. But then these 2 vertices, they have distance 0 to itself and distance the same to any other. So they have no possibility to be identified. So this means that well, there are some Okay, I didn't make the conclusion. There are graphs in which the multi-set dimension of in this way cannot be exactly computed because there are vertices which are not possible to be distinguished by any vertex, by any set. Yeah. So in this case, they have taken the agreement that the multi-set dimension of this graph is infinite. Yeah. So if there are this kind of construction, then the multi-set dimension of the graph is infinite. So immediately we think of one. But there are graphs without first one question. If we have twins, then we have this equation. There are also some other graphs which are having no twins, and they have also infinite multi-set. In general, those graphs are very symmetric. They have a lot of symmetries because it means that whenever that will take any set, you will find a lot of symmetries, so that you will get all these multi-sets which are same, that you cannot identify all these. So one problem which immediately appears is characterizing all graph G such that the multi-set dimension of this graph is equal to infinite. It is an open problem, which I would like to. I have been thinking of it, but not succeeding too much. There are some works on this kind of characterization, but for 3 spots. You can, if you are more interested for this, you can ask. No, yes, you will do. So another thing which is interesting with respect to this is that the existence of only 2 vertices at least that have the same multiset with respect to any set of vertices makes that the multiset dimension is infinite. If I have only 2, then it's multiset dimension is infinite. But I could have probably not 2, but 3 or 4, 100. Yeah. So then counting such vertices is then worthwhile. Namely, if we have a graph in which I know that the multiset dimension is infinite, can we count so many vertices are having this situation that they are kind of these problematic vertices, I could call them. Can we count these problematic vertices? For instance, if we have here a graph which has no any problems anywhere and has these 3 twins, so the number of problematic vertices is 3. Yeah, so that's it, what I want. Maybe we can do that, because if we can do that, we could say, okay, somehow I will define now the S metric, the multi-set dimension equal to the multi-set dimension of this part, and this part I will like to count. This is kind of the generated part of the graph, yeah, with respect to the multi-set dimension. And there are not so many contributions concerning this parameter in general, so it is a topic in which you can work a lot. There are this quite you can work much more. Yeah. So this was done by Inovia, my colleagues. But then it is the time in which we were indeed working this. I even knew that Inovia was working this, and I told her I am working that too, but we are working on this from another perspective, precisely trying to avoid this problem which they are having with the infinite. So what we were doing is that considering something that after we call outer multi-set resolving set, an outer multi-set dimension. Why? Because we don't want to lead to work with these people which are problematic. So try to avoid them. What we do? If there are these such vertices, we include it in the set, but we do not consider the vertices. I mean, we have a set of vertices, again, have the same multi-set representation with respect to the set. And now we said that outer multi-set resolving set is a set such that any 2 vertices outside of the set S have different multi-set representation. This means that I do not care of vertices in my set. So I do not need to care about them. So if I have such kind of vertices, I just simply put them together. Yeah. So then the outer multi-set dimension is the cardinality of the smallest outer multi-set resolving set. For instance, in the graph before is a specific case in which it is the same. Yeah. I can take these 3 vertices, and again we have different multi-set. So yeah, as you see here, I have now the multi-set for them because I do not consider them. I consider only outside. Yeah. In this case, they are equal, and in several cases they are the same thing. But in several cases they are different. Yeah, because we consider only vertices outside. And then we have been working in this topic deeply. And we have now quite a lot of results. In fact, we recently made one article on this, and it is in archive, already not accepted in any journal, and but we are continuing. So first of all, again, it's happening the same, that it is one if and only if it is path graph. Yeah. So the idea is the same, nothing new. Well, here we have not the problem that there exists no graphs with multi-set dimension equal to. Indeed, there are graphs with multi-set, outer multi-set dimension equal to graph. This is something nice from our point of view. And there are some others. Some other reasons. For instance, for any positive integers, the complete graph satisfies that the multi-set, outer multi-set dimension is the order than one, which is clear. You cannot get outside two vertices because they are right. And then we have some different. The only graphs for which the metric dimension only the standard classic one, is equal to the order -1 are the complete graphs. Yeah. But if we consider the multi-set, outer multi-set dimension, then there are some other graphs that are having multi-set, outer multi-set dimension equal order -1. And of course, larger. Yeah. For instance, we have some examples here. If we consider a complete K-partite graph, yeah, in K-partite, in which all the sets of the partition sets are of the same cardinality, so K22, K23, something like that. Then we always get that the outer multi-set dimension of this complete multi-partite graph is equal to 1. I can leave any two vertices outside. If I leave two vertices outside, they are not higher. We have no possibility to distinguish them. Now, some values, for instance, when you consider a cycle, the outer multi-set dimension is equal to 3. And this is probably it's not that clearly immediately. Well, it cannot be 1 because it's path. Yeah. And if you consider two vertices, in a cycle, you will see that always you will get some problems. How? If we are in a cycle, and we consider two vertices which are adjacent, they form a metric basis. But then this vertex, which is adjacent here, and this other one, they have the same ones. This is 1 and 2, this 1 and 2. So 1, 2, and 2 are the same. And if you consider something other that are at far distance, then we have the same, something similar. If they are at distance 2, something in the middle, then again, this which is here and this which is here are having the same distance. If the cycle is long enough. Yeah. And in the last case, you will have vertices which are at distance longer. I mean, at least two vertices here in the middle. Then we consider precisely the neighbor and the neighbor. They have again the same. So it's not possible to have a multi-set resolving set, outer multi-set resolving set. I don't like this terminology. Say 4 words. Outer multi-set resolving set. It is not possible to have 2 in a cycle, so it should be at least 3. I mean, for 3 is not that difficult. You can take 3 vertices from the specific position, and we get a multi-set resolving set. So in this case of the cycle is equal to 3. And one thing that we did was computing the complexity of the problem. And computing this parameter in general is an empty-card problem. Things that it's not that easy to deal with it. And it is even not clear what happened in the case of trees. So if we have a tree, then we don't know what happened. It is possible that it is empty-card also. Okay? So if you are able to prove that for trees is empty-card, this will be a good contribution. For sure you will publish everywhere. Yes. But it seems not that easy for trees. Things. Indeed, I will now take a little moment to dedicate to trees. Yeah. Trees, but not exactly any trees, just some trees. So Which trees? Well, I will take the trees which are called K-area trees. Let's guess what is it. K-area tree is a tree in which you are taking a root of the tree. And then every vertex has the same number of children. 3, 3, 3, 3, 3, 3 is 3. The most popular of them is the case of binary. Thanks very much. 283 for simply binary. So we take K83 rooted in some vertex, the view here. K larger before than 1, of course, because K1 is too small. And then the set of vertices S of this tree is an outer multi-set resolving set if and only if this equation happens. And for any two vertices which are outside of the set S, the distance between U and W is equal to the distance between P and W, implies that they have different multisets representation. I mean, if there are two vertices that they have the same distance to the root, then it means that they have the different multiset representation. The vertices which are here, they have the same distance to the root, and they have, if they have this, then they have different multiset resolving set. It means that the set is an outer multiset resolving. I mean, I do not need to care of vertices which are at different distance. If the vertices which are of the same distance, they have the different distance, implies that they have different multisets. There's a representation, then we are. So we don't need to care about all of them, but only few. Yeah, with this in mind, then what we do is some kind of trying to find some kind of recursive process of how to find to work with this. How it is done? Well, this is a lot of very technical. Probably, I will try to do my best to give you the idea of this. So imagine that we have a tree, yes, and for each, I would say, I will consider only these parts. I would say one part and one part. Yeah, you see that I can create the binary tree in this case and recursive. So with these two trees, I can take another vertex here, join these two, and then I get a tree again, the same idea, and even higher. Yeah. So this is what it says here. We take a set of L larger than 1, and we take K trees, which are full K trees of height L. Then we find ways to disjoin sets. Then we take all the roots of these trees, and then we add another vertex W here, and all the edges here between all the vertices, and all between the root and the new root. I mean, just this process of construction. Yeah. And now we will take S1 and SK, which are outer multiset bases of these trees. I mean, in each of these trees which are below, I will take a multiset basis for an outer multiset resolving set of the smallest possible cardinality. Now, with this basis, I can do the following. Well, this here, what means exactly that? Well, notice that below we're saying if M is a multiset and X is an element of this multiset, M and X brackets represent the multiplicity of X in M. So if we have a multiset, which is 1, 1, 1, 2, 2, it means that the 1 has multiplicity 3 and the 2 has multiplicity 2. So I can write this like 1 to the power of 3 and 2 to the power of 2. Yeah. So what it means that is that in a multiset resolving set, yeah, in each of these trees, I would say, I will look for the multiset representation of the root. Yeah, I will take the root of this vertex of this tree here and the root of this one. I will look for the multiset representation with respect to this set S, which is the corresponding one. And then there I will look for the multiplicity of this vertex in this multi-set representation of this chi of this one means the eccentricity. So I look for the vertex which is at larger distance. Yeah. And if it is happening that all these multisets, all these multiplicities are different, then we will say that the union of all these multisets in each of the subtrees will form a multiset, resolving set in the bigger tree. Yeah. This is in order to do a kind of recursive process. So I will look to a part here, in all these trees, that the union of all of them is a multiset resolving set in the bigger one. Under this condition, yeah, that the multiplicity of the elements which appear in the representation of the roots in each of the trees with respect to the corresponding base will be different. Yeah. If this is the case, then we get that. Of course, this is very difficult because what does mean that I will need to find as many bases as we have here. If we have two in this case, we need to have two bases. Because if we have one basis here and one base which are the same, then these two vertices will have the same multiset representation. So I need one base here and one other base here, different, or totally different. So this is precisely what is happening here. We have a full 83, yeah, again, we take these sets, the union of all of them. If this is happening, then what this is the root. Then for every L larger or equal than N, the outer multiset dimension of 3 is given by this. So this is precisely the union of all of them. I take a set here, one set here, and one in the other. And this is indeed for whatever K. So it's happening for whatever K, not for binary trees or something like that. So what we need to do there? Well, we need to find the smallest n such that the tree is n per k contains k plus 1 of the multiset basis satisfies these premises. It means that we need to find in this kind of tree, for instance, here, this one, we need to find 2 of them. So that I will join one here, because these are the same tree. So I will take one here and the other one here, and then the union of these two will give whatever. But of course, this needs to happen. What I will do, if I will work recursively, for instance, in the case of 2, the first case is different. Here is impossible. Okay, I will consider the next ones. There are 2 here. If I am able to find 2 here, then I'm done. But this is not the case. So I need to go one step more. Yeah. I need to join now these 2 with these 2, and then join more. Here it is. There are now 3. I have it? No. So if I don't have it, then I go to the next step, and so on, until I will find, in one case in which I will find all these necessary outer multiset bases. So this is defining the smallest. So what we need to do is develop a computer program that computes such number. So it will go from the first step to the second one, third one, so on. First, we cannot guarantee termination of this process. We are not sure that this process will end at some point. First, the computational complexity of each of these iterations is exponential on the size of these trees. And second one, even so, we are not able to confirm that this is the case. Probably there exists no this step in which we will find this. Yeah, so this is the problem. Fortunately, for the case in which we consider k equal to, I mean, binary trees, then it is possible to compute that. Yeah, the smallest n which is satisfying this requirement is precisely 4. Yeah, it means that when we have 4, well, this is 1, 2, 3, one bigger. If we have one bigger, then we are able to compute all the required bases. And here we have this. This is the smallest case, what we have in the case of binary tree. So we have a tree which is having height 1, 2, 3, 4. Yeah, the height is 4. And then we are able to find, in this case, 3 outer multiset bases which are different. And so with the situation that the vertex 1 is having different multiset representation with respect to this base. For instance, in this base which we have here, this 2, 14, and all these other numbers, 8 here and all these numbers. The multiset representation of this first vertex is 1, 2 to the power of 2, and 4 to the power of 10. There is also this base, which is 6 here, 8 here, 12, 14, and all these other vertices. They are all different. The multiset representation are different. And it is also this other one, which is 14 here, 8 here, and all this. So for binary trees, this is the smallest example in which we have what we want. And now with this, we need we can go for a step further away. So I form the new graph, and with these 3 bases, I can form what I want. Yeah. As a conclusion, what we get? For the case of binary trees, we can compute, of course, the first by hand. I mean, when L is equal to 1, it's just 1. When L is 2, we have 3. When L is 3, which is precisely this case, yeah, it is 6. And when L is 4, is 15, which is this vertex, this sense. They are having 15 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, and now with this 13, then we apply what we were saying here. You see that the multiset, the outer multiset dimension of this tree is given by k to the power of L minus n times what we get in the stepping. And with this, then it's possible to give, okay, if it is 13 in this step, from now on, we say for whatever L, then it's just 2 to the power of L minus 4, because 4 is the last step, times 13. And we are able to compute all of it. This was a really nice thing. And it was necessary to do some computational things here. That was not made by me, because I am not skillful in cafe, so I didn't do this part, but it was nice. So this gives you one idea that working with trees is really problematic. Really problematic. I have no idea on how to proceed with it. No idea at all. Because even there is this formula for the binary trees, but for k-ary trees, when k is larger than or equal to 3, then it's not there at all. No. Yeah. So, well, it is necessary for to complete the study of trees, find an algorithm that will give multiset resolved set of minimum cardinality for fiber tree, or find an exact formula for outer multiset dimension and solve some problems. In my opinion, I have a feeling. In my opinion, that the most problematic cases are probably the k-ary trees. Why? Because they are very symmetric. If you see them, they are in whatever place that you be, they are more or less indistinguishable with respect to other ones. There are several in the same position. But if you consider the tree, which will be kind of completely unsymmetric, then probably is easier to manage. Because there are not so many symmetries, then you can compute how it's working with this multiset dimension, outer multiset dimension. Okay, the problem computer, the outer multiset dimension is general and mechanics. And now some other things that we were doing are, for instance, the graphs of order n for which the multiset dimension is equal to order 9. This was possible to be characterized. We did it recently. We did this year by June or July or something like that. It is a work with we did with Sandy Glaser and Dorota Pusha, my other colleague, which I was speaking about before. Well, first, it was possible to notice that graph G has outer multiset dimension equal to the order dimension if and only if the graph is regular and the diameter is small. So this was kind of surprising. The proof of it is kind of not exactly easy, but it's nice to follow. Yeah, you can follow it relatively easily. Well, the first key thing is to that we notice that the graph is regular. The graph must be regular because if it is not regular, imagine that you have two vertices which are of different degrees, and you almost immediately can get that it is not possible to have outer multi-set dimension orthogonal graph. Because you can simply construct an outer multi-set resolved set of cardinality order minus 2. There are two vertices. One is having 1 degree, the other one is having another degree. And then I take only these two vertices. So it doesn't matter how the multi-set completely looks like. But this vertex will have, for instance, 1 to the power of 3, and this other one will have 1 to the power of 4. This. Yeah. In the multi-set. Because they have different degrees. It doesn't matter if they are adjacent, because they are adjacent and you're simply counting one less in each case. So they have different multisets. So it is not possible to have a graph which is not regular. It must be regular. Now, to prove that this diameter is at most 2, then it's more technical, but it is also nice to see. It is interesting thing, and it is kind of interesting proof that because it's also kind of didactical. It can give you an idea on how to work with it. Yeah. Examples of this, well, complete graphs, of course, because are of that one of diameter 1. There are complete multipartite graphs whose parts are of equal cardinality. For instance, what we were speaking about before. Cycles C4 and C5. Namely, the Petersen graph, which is sometimes a graph which is doing something that he is behaving different from anyone. It's like he is special. Side to what he wants. Well, in this case, he had to enter by the simple. Yeah? Hamming graphs, which are Cartesian product of this graph. Remember that in the case of metric dimension, finding the metric dimension of Hamming graphs is still open. But for the multisets, we are protected. It's okay. Direct product of complete graphs, the same thing. So these are some examples. I mean, there are some other ones clearly that you can find that are satisfying this problem. Well, all of them which are regular and not regular. Yeah. Then other things that we were doing, I'm going time, is for instance graphs with multi-set dimension equal to outer multi-set dimension. I always forget side different. While the multi-set dimension is not possible equality 2, yeah, for the outer multi-set dimension it is possible to have equality 2. But it seems that it's kind of more or less the same like metric dimension. Remember that metric dimension, I was saying that it's not that easy to characterize all the graphs. Well, here it seems that somehow it is more or less the same, but we can go a little further. To do that, there are some properties first that we were able to prove. For instance, if we have a graph which is having outer multi-set dimension equal to, and S is an outer multi-set basis, then there are some properties. For instance, the degree of these two vertices must be at most 2. It cannot be more than 3. Yeah. And then we also define some things like that. When we have a graph, and then for every k graph and a set x of vertices in the graph, and for every k larger or equal than 0, we represent this set as follows. Lk of x is the set of vertices such that the minimum distances between u and x is equal to k when x is equal to x belongs to x. For all the vertices that are at distance 1, at distance 2, at distance 3, to all the vertices of this set. Not to all of them, but to at least one of them. Yes. So of course the case L0 is equal to x. And of course, the union of all these sets form a partition of the vertex set. So if we have this definition, then for every k larger or equal than 1, these cardinalities of sets should happen. Yeah. Of course, under this assumption that we are having a graph with outer multi-set dimension equal to and the set S. So we see that all the cardinalities of all the vertices of all the sets at distance 1, 2, 3, 4, somewhere is at most 3. Yeah. And moreover, for any S of this set, if there is a set which having partition some cardinality, then the other one is having a smaller or equal. Yeah. And moreover, if the set S is formed by 2 adjacent vertices, it means that if you appear adjacent, then the cardinalities of all these sets is at most 2. So this is immediately giving more information about that, those graphs. So we can characterize them, how they look like. For instance, consider the following family of graphs. We have a graph G, which is in the family F, and they have this set of vertices, U1 to UR and B1 to BS. For some BR at least 1 and S at least 2. And the edges are all the B, U1, B1, U1, B2. And for all this, this equation, I will explain now better over here. Something like that. If we have a set of two vertices that are adjacent and we form all these U1, U2 till the end and V1, V2 till V somewhere. And then there exist these edges. This edge must exist. All these edges here must exist also. And these edges here can exist or not. For instance, this vertical edge can exist or not. And this edge for a kind of diagonal can exist or not, like here exists, but here no, here no. But these kind of edges, which are diagonal but in other direction, never exist. Okay? And it could happen also that one will go further away as we want, and the other one will remain here. So in this case, we were able to prove that a graph G has an outer multiset basis formed by two adjacent vertices if and only if the graph is in this form. So this is a characterization. Yesterday, someone was asking me about why the characterization, what means, why we characterize. Well, we can characterize something if we give exactly how the graph looks like. So it's not like I would say, okay, this is characterization. We say that this equation happens if and only if there are some 5 conditions. Okay, there are some 5 conditions that I have to check. But this is not exactly clear. How this condition could be so difficult that probably is easier to check the other. And here, okay, I am having the multiset. I know that this is happening when we have this graph. And this graph are not that difficult. We can be recognized very easily. Yeah. Now, the case in which we have two vertices that are not adjacent, but they are more complicated. So, well, even there is an algorithm. Okay, this is, I didn't speak, I think that I didn't write it. The case in which we have outer multispaces that is not formed by two adjacent vertices, I mean, they are something other, then this is not, it seems that it's not exactly clear, but it is somehow somewhere in this time. We can probably get some construction and give some ideas and maybe somehow can be drawn, but I think that will be a lot of time consuming and will, if that's not deserve much more. So we just keep doing that. But what we develop is an algorithm. There is an algorithm which is saying that the problem of deciding whether we have a graph that satisfies this can be polynomially known. Doesn't matter if it's adjacent or not. We can always use this algorithm and know the solution. So with this, we are kind of done, I would say, with this problem. Probably it's nice to consider the other case when they are not adjacent. I would say that it does not deserve attention. Yeah. Now, other things, what we did was considering some kind of product graphs. Since I am a little out of time, I will skip this part about lexicographic, and I will go on into the case of grid. In the case of the grid graphs, it is something kind of difference with respect to the metric dimension. Remember, yesterday I was speaking about the grid, and the metric dimension equals 2. So we were taking only 2 vertices in the corner. It was 2 below. Yeah. Here we were considering the grid. 2 vertices which are in these positions, and they, for instance, can be here or here. Right? And this is a metric basis, and the metric dimension of this graph is equal to. But in the case of outer multiset dimension, then it is not possible to have this, because if we consider a resolving set in the standard way, then it's formed by these 2 vertices. But you can easily see that if I consider this vertex and this vertex here, then they are having the same multiset. Even more than this, if I consider this here over and this here over, also they have the same multisets with respect to these 2 sets. And there are a lot more that are having the same multiset. So it cannot be 2, because it is impossible to find 2 vertices that will be outer multiset. So it should be at least 3. Then what we need to do is to find a set which would be an outer multiset, so a set of cardinality. And then what is possible to do? Well, it cannot be at least 2 because of this what I was saying. It is not bad, so it cannot be 1. And there is no graph with equal 2, so it can be at least 3. So this is the first part. Now we will consider a set formed by 2 consecutive corners, which are, for instance, well, by 1, 1, R1, I mean this vertex here is 1, 1, and this R1 is this thing. Together with the vertex 2, 1, I mean this 2, 1, 2, 1. This. Okay, when we have small cases, for instance, the path here below is just here, then we need to consider some other cases. So considering these 3 vertices, then we have some properties that we can use. First of all, we know that these 2 vertices in the corner, they form a resolving set in standard way. Yeah, it means that they identify all the vertices of the grid by using distant vectors. Yeah, all the vectors are different. So by this we mean that if we have a vector, for instance, this vector is distance 1, 1, 2, 3, 1, 2, 3, 4, 4, 3. Yeah. Now consider that we have this vertex. Now, if we consider any other vertex, for instance, this one here is having distance only to the corner, to the resolving set. Is distance 3, 2. Yeah. So this kind of vertices, I don't need to care about that. Because one, it doesn't matter what will happen in this one, then this will be the competitive with respect to the. So we need to consider only those vertices whose distant vectors become equal once we transform them into distance multiset. I mean, so like I can switch. Yeah. If they have here distance 1 and 2, and the other one 2, 1, then it's problem because when I will transform them into multisets, they will be different. They will be the same. So I need to consider what is that. And then in this case, we need to see that we need something more. What we need? Well, this, for example, 2 lines. And with this, we get the solution. And it is possible to go. Well, it's not that simple, like it said there. It's like technical, we need to do a lot of cases, considering what's happening because this exchange position with the other. Yeah. You can see it given the internet already. But it is possible to give a solution to this grid gas. And now some other questions that are here are, for instance, these ones. I would like to characterize all the graphs which are having the multi-set dimension equal infinite concept. And for those ones which are having infinite multi-set dimension, I would like to know which is the number of vertices that are problematic. This one, which are creating problems. This is something that I would like to do. Also, the proof of NP hardness of computing this value, the multi-set dimension in the starting name. For the other one, it's not. And for this one, it should be like the same. This is the reason that I say find a proof of the NP hardness. What is that? I'm not saying which is the complexity. I just say that find a proof for it. Also, finding the outer multi-set dimension of some interesting families of graphs, like for instance, the torus graphs, cylinders, hypercubes, planar graphs, trees, many more. Characterizing the graphs for which the multi-set equals the outer multi-set dimension, or developing some linear programming models for the outer multi-set dimension of graphs. And also, finally, is it the case that computing the outer multi-set dimension of a tree is indeed NP-hard? I suspect it's the case, but I'm not sure. So it would be nice to have something like that. And many other ones, because there are a lot of things here to do. It's widely open. So any contribution there will be nice. It will be welcome and will be published everywhere. So some references are, for instance, this is the last edition we did for the contribution on outer multi-set dimension of graphs. You see it on 2022. This is the first work on the outer multi-set dimension, and these are the works which are on multi-set dimension of graphs. First from Yero, and the second one which is working with trees. I have not seen any more things on multi-set dimension because there exists also local multi-set dimension, but it's not multi-set. Yeah. So things are just things. So as you see, there are only these 4 words. So you can still have plenty of sense to do confusion. And that's it. Thank you very much. If you have questions, please.
Any question? Any question from the audience? Yeah.
Is there any information about other definitions or
No, this is not. If there will be, I will complete the speech. I was speaking here about everything. So what I didn't speak here, it's not. Well, I didn't speak about lexicographic case, but it is in that slide. Anything other is not.
Are you going to share this slide?
Well, I already sent to. You have it. It's just mine. Yeah, I sent to list of all the slides from yesterday, from today, and from.
So for the N-1, so it's supposed to be regular and with diameter at most 2, right?
Yes.
Yeah. So for the multi-set dimension without the outer, the dimension will be infinite for that one.
Was that on the way?
Yeah, because because for small diameter, it's always infinite for diameter at most 2. So have you think about like the other graph with small diameter but not regular?
What happened when this small diameter but not regular?
Yeah. It's still open?
Yeah, it's open. I think that when we were working together with Sandy about this, we were trying to think about it, but probably we didn't go deep on it, or probably was much difficult and we just kept doing it.
Yeah.
I don't remember exactly, but I remember we were trying to think about it, but didn't continue in direction. But we are still working on this, so probably at some point.
Because I think it will be interesting because it is infinite in the sense of multi-set, but then when we exclude the ones in the resulting set, then it becomes.
It makes sense that it's infinite for your case.
Okay.
Because distances are not too many.
Yeah, but your result is surprising for me.
Yeah, it was indeed surprising for me when we were doing it. At the beginning, in our first work, we were just finding some examples in which there are enough which are having order -1 in the value, but they are not the complete graphs. Okay, same that like that. We probably tried to find all of them, but didn't think. But now then we decided that we were going deeper on things, and then we realized that we were having a lot of problems, I remember, on how to proceed with that. But the key point was this, to observe that they were effective. Once you get that, then everything went. It is now easy. You see that it's very natural. You see this thing, makes no sense. Yeah, but at the end, it's not that sense. And once you have that, then you get a lot of problems because the graph is regular, you know that.
Any other question or comment?
Then we have multi-set dimension. Then what was the motivation to define this new parameter? Or what is the significance of parameter?
Well, in my case, because I told you, we began to work at the same time, I think. She was working in her direction and my motivation was just like to change. I think at some point I was thinking, okay, we are considering vectors all the time. And I was speaking with some colleague from computer science, this guy, Rolando Trujillo, I'm sure. He's indeed, again, also my home country. And he was telling me that in computer science, because he is computer scientist, so she's thinking like a computer scientist. You know, in computer science, many times you have no idea about kind of orders. You don't know what will happen. You know, in a graph, you are here and you have no idea if you should go left or right or left. So you cannot consider vector because this is not set. So you should consider something that will be more than a vector. Okay, so probably better to consider something more general. Then, okay, so then most of this change in matrices. Then he gave this idea and we began to work like that type of thing. So Fernando and this other two guys. This other one is student of this one, and this one was. We are all Cubans. All these four guys. And then we came out of this. And the case of Ilovian has some kind of story about why they started to this maybe you answer.
I think it's very similar because
Yeah,
like
you're right
for the metric dimension, the resolving set has to be ordered set. And we want to release that condition.
Yeah, but
so,
in your paper you are writing about some email which you received.
Yes, yes. Yeah, so but his motivation is also.
Okay. So this is the main motivation. Just to check to do something different. You know, we are not with this. Someone first. Yeah.
If we say to consider resulting vertices, like
You consider
the resulting to have a resulting set, so we could set of vertices. But maybe now you want to like count twice for your set.
I don't get you.
So you have a resulting set like this. Like this vertices.
Resolving set in the standard way or multi-set?
In any case, let's say this is the same. Maybe now you want to count one of the vertices twice. Like you have one set of results, the resulting set and the resulting multi-set. So okay. So you count like the distance from a vertex reading this reverse when correct in the formal set. What if you choose like two vertices like to be the same in the resulting set?
How that will be the same?
It's a good set.
Okay. Okay, that I will say that I will look for the property that the vertices will have not different but the same. What is that you mean?
No. He's talking about instead of taking different elements in the resolving set, why are you not taking the multi-set as a resolving set? If you do that, then what will happen? We are taking multi-set as multi-set representation. But he is talking about the resolving set as a multi-set. Yeah.
The resolving set as the multi-set.
Yeah. Instead of taking a set, like we have repetition of words.
No, still I don't get it.